This video will give you a brief introduction to nuclear magnetic resonance. Now, we will be covering this topic much more extensively in Chem 227. However, if you're curious about reading up on any of the details of nuclear magnetic resonance, more information is found in Chapter 15 in the textbook. Nuclear magnetic resonance, or NMR, is a powerful technique that can help elucidate or verify a chemical structure. Now, NMR is a type of spectroscopy, and we've learned already about IR spectroscopy that can detect for the presence or absence of bonds in a molecule. Now, where IR looks at bonds, NMR is going to be focusing on atoms, and specifically we'll be looking at atoms that contain an odd number of protons and neutrons, or an odd mass number. Since hydrogen and carbon are the main types of atoms found in organic structures, hydrogen and carbon are the main atoms that will be looked at in organic chemistry NMR. So for H1 NMR, which is also known as proton NMR, this H1 means that we have a hydrogen atom that contains one proton and no neutrons. H1 is the most common or abundant isotope for hydrogen. Carbon-13 contains 6 protons and 7 neutrons. Now, carbon-12 is the most abundant isotope of carbon. Carbon-13 only makes up about 1% of carbon atoms that exist. However, since carbon-13 is the only carbon isotope with an odd mass number, it's the only one that's detectable by the NMR machine. So carbon-13 is known as carbon NMR. Now, in this video, we're going to be focusing mainly on proton NMR because proton NMR is the most useful for detecting organic structures. I will briefly introduce carbon NMR and we'll see how that can be somewhat useful. Atoms that have an odd mass number also have a magnetic spin. So you can think of them as little globes or little Earths that have a north pole and a south pole, and they rotate in different directions. Now, each of these arrows represents the atoms, and as you can see, in the absence of a magnetic field, there really is no set direction that the atoms are capable of spinning in. Now, when you take all of these atoms and you put them in an NMR machine applies an external magnetic field. So in this box here, the blue arrows represents the magnetic field that's been applied by the NMR machine. Now, when this field is applied to a set of atoms, what's going to happen is the atoms' spin are going to align with this magnetic field. Now, if they are completely parallel, meaning they're going in the same direction as the magnetic field of the machine, this is known as an alpha spin state. However, if they've been aligned and their spin is opposite the direction of the magnetic field, this is known as the beta spin state. Now, the alpha spin state is a lower energy state because we're not fighting against the magnetic field of the machine. The beta spin state, because it's in the opposite direction, has a higher energy. Now, once these atoms are aligned with the magnetic field, the machine is going to push radio frequency radiation at the atoms. And the atoms that are in the alpha spin state are capable of absorbing that radiation and moving up into the beta spin state. So as the protons absorb this frequency, they're capable of flipping back and forth between the alpha and beta spin states. Now, the amount of radio frequency radiation that's absorbed is completely dependent on the proton's electronic environment. Essentially, how much electron density is around the atom. This is an example of an NMR spectrum. On the x-axis here, we have chemical shifts in units of ppm, which correspond to the amount of radiation absorbed by the protons relative to the standard TMS. The different peaks that we see represent protons. Now, the peaks that appear on the right that are closer to 0 represent protons that are shielded. and shielded means that they're surrounded by a lot of electron density and unaffected by the radiation. Now, TMS stands for tetramethylsilane. It has this structure. And we can consider the hydrogens that are on TMS to be the most shielded protons. So any other protons that we have in organic molecules will always be a little bit more de-shielded than these ones. Now, peaks that appear on the left in an NMR spectrum, so over here, these are known as the d-shielded protons. Now, d-shielded protons are not surrounded by a lot of electron density, which makes them more affected by the radiation. Now, in general, chemical shifts go up to about 14. We usually mainly see things up until about 8, but there are a few, as we'll see in future slides, a few types of protons that do appear past that 8 region. So we'll be focusing on chemical shifts from 0 to 14, and we'll go over this in much more detail in later slides. NMR is capable of telling us 4 different things about a chemical structure. We'll go through each of those 4 things separately, however, we'll use the same molecule as our example. So the first thing that NMR can tell us is how many different types of hydrogens there are. When I'm talking about types, I'm meaning hydrogens that can be described differently. So let's go ahead and take a look at these 3 hydrogens here. So these 3 are connected to a carbon that is connected to a C double bonded to an O. Now there's no other hydrogens in this molecule that can be described exactly the same way. These 2, even though they're connected to a carbon that are connected to a carbon with a C with a double bond to an O, they're also connected to another carbon that has a single H. So these guys are different than these ones. They have a slightly different description. So we'll go ahead and call these type 1. These 2, which have their own description, we'll call type 2. Then we'll move on to the other hydrogens. So this single one is bound to a carbon that's bound to 2 methyl groups as well as a CH2 group. There's no other hydrogen that has that exact same description, so we'll go ahead and call this type 3. Now these 3 are connected to a carbon that's connected to this particular CH. These 3 are also connected to a carbon bound to this particular CH. So both of these 3 sets of hydrogens have the exact same description, which makes them the same type of hydrogen. So we'll go ahead and call these type 4. Now, since we have 4 types of hydrogens, each set of hydrogens is going to have its own set of peaks on the NMR spectrum. So 4 types of hydrogens means that we would expect to see 4 different peaks. On the NMR spectrum. And here's an example of what the NMR for this compound looks like. So as you can see, we've got a peak here, there's a set of peaks here, there's a single peak there, and a peak there. We'll talk about why they're different heights and why you see multiple little splits in later slides. But overall, we have 4 peaks on the spectrum, which correspond to our 4 different types of hydrogens. Now we just saw that our molecule contains 4 different types of hydrogens. So we have type 1, 2, type 3, and then our type 4. Now the second thing that NMR can tell us is the relative amounts or number of hydrogens of each type. This is shown in the peak height or the area under the curve, which is also known as the integration. Now thankfully for us, Most of the NMR processing software will do all of this calculation for you. It'll actually measure the area under the curve and tell you how many hydrogens correspond to those particular peaks. Okay, so let's take a look at our example. Now in our type 1 hydrogens, we have a total of 3 H's. In our type 2 hydrogen, we have a total of 2 H's. For type 3, we have a single H. And type 4 is composed of 6 hydrogens. So for this molecule, we would expect to get an NMR spectrum that looks something like this. Now, as you can see, we have the number of hydrogens written above each peak. So that means that these sets of peaks correspond to those particular groups of hydrogens. So for our 6 hydrogens, that's going to be type 4. They are represented by this peak here. For type 3, which is a single hydrogen, it's going to be represented by this set of peaks. Type 1 will be the 3 hydrogens. And type 2 will be the 2 hydrogens here. Okay, so that will help us assign each peak to each group of hydrogens. The third thing that NMR will tell us is the number of neighboring hydrogens to a set of hydrogens. This is also known as splitting patterns. Now, when I'm talking about neighboring hydrogens, we're focusing on neighbors that are on an adjacent C. Now, for neighbors or splitting patterns, we use what's known as the N+1 rule. And the N+1 rule says that N, which is our number of neighbors, plus 1 will split the peak representing that group of hydrogens into that set amount. Okay, so let's take a look at our first example. Now we know that these 6 hydrogens are represented by this peak here. We saw that on the previous slide. So for these 6 hydrogens, let's take a look at their neighbors. Now on the carbon adjacent to these hydrogens, which is right here, we have a total of 1 hydrogen neighbor. So using our N+1 rule, we'll say that 1 neighbor plus 1 means that our peak for those 6 hydrogens will be split into 2. So we'll go back over to our spectrum and we see that our peak has 1, 2 little splits, or two little, it's been split into 2 mini peaks. This represents a doublet. And a doublet means that these group of 6 hydrogens has 1 neighbor. Okay, now let's come over to these 3 hydrogens. Now we know that these 3 are represented by this tall peak over here, as we saw on the previous slide. Now looking at the neighbors for these 3 hydrogens, we'll focus on this carbon. This carbon contains no hydrogens, so that means these 3 have no neighbors. So using our N+1 rule, we'll say no neighbors plus 1 means that our peak will be 1. It will not be split at all. So as we can see, this is a single peak. It has not been split in any way, shape, or form. This is known as a singlet. And a singlet means that those hydrogens have no neighboring hydrogens. Okay, now let's take a look at these 2 hydrogens here. Now these two hydrogens have two neighboring carbons. We have a carbon with the double bond O, which has no hydrogen neighbors. And then we have another carbon with a single H. So these two hydrogens here have one neighbor. So using our n+1 rule, 1 plus 1 equals 2. So we saw in our previous slide that these two hydrogens were represented by this set of peaks here. We'll see that this peak is split into two. So again, we have another doublet, which means that these two hydrogens have one neighbor. Okay, now lastly, let's focus on the single hydrogen here. Now for our single hydrogen, we have three neighboring carbons. We have a carbon with three hydrogens, we have another carbon with three hydrogens, and we have another carbon with two hydrogens. So this H here has 8 neighbors. So our n+1 says that we would expect the peak representing that H to be split into 9 little mini peaks. Now the hydrogen that represents the peaks are here. Now it's very difficult to show 9 splits on an NMR spectrum, and it's not always going to be that clear. But what we can see is we have a set of splits representing that one hydrogen where we have many, many, many splits. This is known as a multiplet. And a multiplet just means that this hydrogen has lots of neighbors. So this is a very useful tool for knowing where hydrogens are in a particular molecule. The last thing that NMR can tell us is the type of chemical environment the proton is in. Now, in general, our base is alkanes, which are hydrocarbons, and hydrocarbons fall in the 0.7 to 1.5 ppm range. And alkanes, we can just think of are kind of the base. They're very shielded. Anytime we add any other atom to the molecule or any other functional group, we're just going to decrease the shielding and make it a little more de-shielded. Now, putting protons or alkyl groups next to electron withdrawing groups or electronegative atoms, for instance, will move them further downfield or to the left into the more de-shielded region. So let's take a look at our example. We have a whole bunch of carbon and hydrogens, but we also have the presence of a carbonyl. Now, a carbonyl has an oxygen, which is an electronegative atom, so the oxygen will be drawing electron density towards itself. And anytime we have electron withdrawing groups or electronegative groups, we're going to move the peaks representing those hydrogens that are close to the group further to the left. So we saw that these three hydrogens were represented by this peak here. These two were represented by this peak here. This guy was represented by this peak. And these 6 were represented by that one. So the 6 hydrogens are the ones that are the furthest away from the carbonyl. So as you can see, the peak representing those 6 hydrogens are within the range of a regular alkane. What this means is the electron withdrawing group has a very little effect on these hydrogens, so they are still very shielded. Now, as we get closer to the carbonyl, so this single hydrogen here is a little bit closer than the 6. And for this single hydrogen here, it would normally appear at a 1.5 ppm if there was no electron withdrawing group present in the molecule. But since there is an electron withdrawing group and it is closer to this single hydrogen, this peak now appears at 2. So it's been shifted about half a ppm to the left. These two hydrogens, which normally come out at around 1.3 or so ppm, are even closer to the carbonyl or electron withdrawing group than our single hydrogen is here. So with these guys, we see a big shift from about 1.3 to about 2.3. So a full chemical shift to the left. And then for these three, which are also very close to the carbonyl group, they would normally come out at about the 0.7 or 1.0 ppm range. And since they're so close to the electron withdrawing group, they're going to be shifted over to about 2.2. So you will be able to use and print out the proton chemical shifts table. So similar to the IR stretches or IR frequency table that I provided to you a couple weeks ago, this will help you figure out where the protons can be found on NMR spectrum. So unlike the bonds that we focused on for IR, this is going to be focusing on hydrogens. So if we look in each example, we have hydrogen, hydrogen, hydrogen. These are the hydrogens. Anytime you see an H, this is what these numbers are representing. So you can actually just go through and underline all of them. Now, I just spoke about alkanes having chemical shifts in that 0.7 to 1.5 range. So these three, the CH3s, CH2, and CHs, these will represent the the hydrogens found on carbons in alkanes. So anytime you have just a regular CH3, comes out around 0.9, CH2 is around 1.3, and CH is around 1.4. And again, these are approximate chemical shifts. Now, as we saw previously, if we put these H's next to an electron withdrawing group, so for instance here, we have a CH3, which is similar to the CH3 there, but we're showing that it's connected to a carbonyl, which is electron withdrawing. So we see the big difference from 0.9 to 2.1. If you put a CH3 group next to a benzene ring, it's going to have a huge effect as well. And so we will expect those types of peaks to appear at 2.3. If we put a CH3 right next to a double bond, that's also going to have an effect, and we're going to shift it from 0.9 to 1.7. So all of these are just showing different scenarios for CH3 groups that are connected to different things. Let's see. Hydrogens that you want to make a note of are ones that have very high chemical shifts. So for example, an H directly bound to a benzene ring appears at 6.5 to 8 ppm. These are really the only types of hydrogens that will appear in that region. If you have an aldehyde hydrogen, so one that's connected to a carbonyl, that's going to appear at 9 to 10 ppm. For H's that are directly connected to electronegative atoms, such as in amines, alcohols, phenols, or carboxylic acids, those tend to show up at different places on an NMR spectrum. So for amines, a peak representing an H directly connected to a nitrogen can appear anywhere between 1.5 and 4. For alcohols, it's usually around 2 to 5. For phenols, 4 to 7. And then carboxylic acids actually appear at 10 to 12. And this is an important one to remember because this is really the only type of hydrogen that can appear in that particular region. As with everything in chemistry, there will always be exceptions. So for NMR, the main two exceptions are first, to the types of hydrogens. We will see exceptions with hydrogens bound to benzene rings. So if we take a look at this example, we have a benzene ring with an ethyl group attached to it. Now there are 5 hydrogens on the benzene ring. And if we think about each of the hydrogens and their proximity to the ethyl group, we'll see that they can be described differently. So our first 2 hydrogens are the closest to the ethyl group, so these are considered the same type. These next 2 are a little bit further away, and so those 2 would be considered the same type. And then the last one is the furthest away from the ethyl group. Now most peaks representing the hydrogens attached to benzene rings are in a very deshielded range of about 6.5 to 8 ppm. Because these are so deshielded, their proximity to the ethyl group does not affect where the peaks will appear. So actually, all 5 of these hydrogens are considered one type and will all appear as one set of peaks. Okay, so we mainly see that with hydrogens attached to benzene. The second exception is to the n+1 rule, or the splitting or neighbor rule. And this will occur when we have hydrogens bound to electronegative atoms or right next to highly electron withdrawing groups. So main exceptions to these rules are hydrogens attached to oxygens, so in alcohol groups, when we have them attached to carboxylic acids, hydrogens involved with aldehydes, and hydrogens attached to nitrogens in amines. So these peaks will always appear as one peak. They will have no splitting. So we do not look at the neighboring rule with these types of hydrogens. Now we've gone over our proton NMR and all of the different things we can look at that help tell us a bit about the structure of the molecule. Carbon NMR is not as in-depth. Carbon NMR can really only tell us one main thing, which is the number of different carbons that we have in a molecule. Mainly, how many different types of carbons we have. So if we take a look at our example molecule that we've been using throughout this video, we'll go ahead and circle all of the carbons, and then we will describe them. So now with carbon NMR, we are focusing on carbons. So first, we want to go ahead and describe them. We have a carbon in a CH3 group directly connected to a carbonyl. So that is the only carbon that can be described in that exact way. So that's going to be type 1. We have the carbon in the carbonyl, which is the only one. So that'll be a second type. We have a carbon in a CH2 group that's connected to a carbonyl as well as a CH. Again, that's the only carbon that can be described in that exact way. So that's type 3. We have the carbon of the CH group that is connected to 3 other carbons. It's the only carbon with that exact same description, so we'll call that type 4. Now our last 2 carbons, we have a carbon connected to 3 H's that are connected to this CH group. The exact same description could be said for the carbon on top. So again, very similar to the hydrogens, but this carbon and that carbon are exactly the same, and they would be their own type of carbons. And that would give us our 5th type. So we've got 5 types of carbons, which means we expect to see 5 peaks or signals. And if we take a look at the carbon NMR, that's exactly what we see. So as you can see, these peaks are not split. They do appear at different chemical shifts. We won't really focus on that, but we have a total of 5 peaks. So that's really the main thing that we use carbon NMR for, is to figure out how many different types of carbons we have. Then we can use that in conjunction with the proton NMR to actually put together a structure of the molecule. There are 2 main types of NMR problems we're going to encounter in organic chemistry. In the first type of problem, you are given the molecular formula of a possible molecule, and you are also given its NMR spectrum. From these 2 pieces of information, you would be asked to draw or determine a structure that matches both of these pieces of data. This is a very complicated type of problem, and it's something that we're really only going to be doing in Chem 227. However, to get us started on these types of problems, we're going to be practicing calculating the degree of unsaturation. Now, a degree of unsaturation tells us how many pi bonds and or rings are possible in a molecule based on its molecular formula. Now, the degree of unsaturation calculation involves taking the molecular formula and plugging in the numbers into this equation. So we do 2 times C, where C is the number of carbons in the molecule, plus 2, plus N, which is the number of nitrogens, minus X, which is the number of halogens, minus H, which is the number of hydrogens. We take all of that and we divide it by 2. So write down this formula. We're going to be using it in the first part of our worksheet today. And on the next slide, we will do an example of the degree of unsaturation. So let's go ahead and calculate the degree of unsaturation for a molecule with the molecular formula C3H4. So first, we'll take 2 and multiply it by the number of carbons, which is 3. Then we'll add 2 to that. Then we will add the number of nitrogens, which there are none. We will subtract the number of halogens, which we don't have. And then we'll subtract the number of hydrogens, which we have 4. So we'll take all of that and divide it by 2, and we end up with a degree of unsaturation of 2. Now, a degree of unsaturation of 2 means a few different things. It means that we can have 2 pi bonds, or we can have 2 rings, or we can have a pi bond and a ring. Now, with only 3 carbons, it's unlikely that we're going to have 2 rings because it's not possible to make 2 rings out of 3 carbons. But let's go ahead and think about what it means to have 2 pi bonds. With 2 pi bonds, it means that we can have 2 double bonds. Since each bond in a double bond is a pi bond. It also means that we could have 1 triple bond. Since 2 of the bonds in the triple bond are pi bonds. Or it means that we can have 1 ring and 1 double bond. So it can mean a lot of different things. So let's go ahead and draw 3 constitutional isomers that are connected differently but also still incorporate the 2 degrees of unsaturation. So for 2 double bonds, we'll take our 3 carbons, connect them with all double bonds, then we'll go ahead and fill in our hydrogens. And really calculating this degree of unsaturation helps us keep track of the electrons, making sure that we draw structures that have no formal charges. So that's one possible structure that could fall under this molecular formula. We could also have a structure with a triple bond. Again, we want to draw structures where we have no formal charges. We could have a ring and a double bond. So we'll connect all 3 carbons in a ring. We'll put a double bond between one of them. And then fill in the hydrogens. Okay, so these are 3 possible structures that could have this molecular formula. Now, if we were given an NMR, we would be able to use all of our knowledge from NMR to match one of these structures to the NMR spectrum. Now, just a couple of notes about degrees of unsaturation. If you have a degree of unsaturation equal to 0, that does not mean there's no molecule. 0 just means there are no pi bonds or rings, which means every molecule you would draw with that degree of unsaturation would be composed of all single bonds. Another thing to note is oxygen does not affect the degree of unsaturation. So you'll notice that oxygen is not incorporated into the degree of unsaturation formula. So anytime you're presented with a molecular formula with oxygen, you just ignore it in the calculation. And finally, if you have a degree of unsaturation equal to 4 or more, plus you have a molecular formula that has 6 or more carbons, all of your structures will incorporate a benzene ring. So benzene, if we take a look at it, is made up of one ring plus 1, 2, 3 pi bonds. So a benzene ring itself has a total of 4 degrees of unsaturation. So just keep that in mind when you're doing your degree of unsaturation calculations in the worksheet. If you come up with 4 or more, just know that all of your structures will involve a benzene ring. The second type of NMR problem is when you are given possible structures plus a proton NMR spectrum, and you're asked to match structures to the spectra. And we can do this just by using the process of elimination. So this is a much simpler type of NMR problem, and this is mainly what we're going to be doing in the worksheet today. So here's just a suggested process that you can use to help you narrow down your possibilities. Since we have the 4 different factors of NMR spectra, this can kind of help you figure out which one to use. So first, take all of the structures that are given to you and determine the number of different types of H's in the chemical structures. That's the first thing that will make sorting through the data a lot easier. Second, narrow down possibilities to molecules that have the same number of peaks or the same number of different types of hydrogens. Step 3, match the number of hydrogens to the integration. So if you have a molecule that contains 3 types of hydrogens, where you have 1 hydrogen in one group, 2 in another, 3 in another, then you'd want to make sure that you have a spectrum that has those same numbers. And then 4, if you need it, look at the chemical shifts or the splitting or both to narrow down further and confirm a choice. So we'll go ahead and look at an example on the next slide. So in this example, we are given 4 possible molecules, and we have to match one of these to this NMR spectrum. So first, what I'm going to do is I'm going to go ahead and go through and draw in all of the hydrogens that we can't see in these bond line structures. So we have one that we can't see here. We've got 2 here, and 3 here. For the rest, I'll just go ahead and draw lines. We have 1, 2, 3. We have a single one there, 1, 2, 3, and then of course the one attached to the oxygen. On our third structure, we have 1, 2, 3, 1 there, 2 here, and 3 there. In our fourth structure, we have the 1 on the oxygen, 2, 2, and 3. Okay, so now let's go through and figure out how many different types of hydrogens we have. Well, in our first structure, we have the 1 attached to the oxygen, so that's one type. We have the 2 that are closest to the alcohol group. So these are different than these 2 because the second set are further away. So we've got 1, 2, 3 types, and then the 3 hydrogens at the very end are the furthest away from our alcohol group, so that'll be 4 types. In our second structure, we have the hydrogen attached to the oxygen. The single hydrogen that is closest to the alcohol group. And then now the 3 at the very end are the same. They're the same distance away from the alcohol, and there's really no difference when we describe them. So in this structure, we have 3 types of hydrogens. In our third structure, we have 3 hydrogens here, which are closest to the bromine. They're different than the 3 hydrogens on the other side, which are an extra bond away. So already we have 2 types. We have the single hydrogen closest to the bromine, and then the 2 hydrogens that are on their own. So again, we have 4 types of hydrogens here. Okay, now for our last structure, we have the hydrogen attached to the oxygen. We have the 2 hydrogens, which are closest to the carboxylic acid group. 2 that are a little bit more further away, so those would be 2 separate groups. And then our 3 hydrogens at the very end are the furthest from the carboxylic acid. So we have 4 types. Now, looking at our NMR graph, we have a total of 4 peaks. Remember, the 4 peaks means 4 types of hydrogens. So already, we can get rid of this as one of our possibilities. Okay, next, let's go ahead and look at the integration or the relative types or relative number of hydrogens in each type. So for our first molecule, we have 1 hydrogen, 2, 2, and 3. For our third, we have 3, 1, 2, and 3. And for our fourth structure, we have 1, 2, 2, and 3. Now taking a look at our NMR spectrum, we have 2 hydrogens, 1, 2, and 3. So we want to find structures that contain a set of 3 hydrogens, 2 sets of 2 hydrogens, as well as a set of 1 hydrogen. So our first structure can fall under that category. Our third does not work because we have 2 sets of 3 hydrogens. So we'll go ahead and cross that out. Our fourth structure can also be considered because we have 1, 2 sets of 2, and 3. Okay, so now we've narrowed down our possibilities even more. So last, let's take a look at the chemical shift. Now, one of the main points of focus is the fact that we have a carboxylic acid. Now, carboxylic acid hydrogens are one of the most d-shielded types of hydrogens. These come out at ppms of around 10 to 12. Now, if we look at this NMR graph, all of these peaks come out between 0 and 4. So that means that this cannot be our structure, and this guy is our final structure. Now let's go ahead and verify it. Even though we've done the process of elimination, let's make sure everything matches. I'm going to go ahead and erase all these marks. Okay, so I'm going to label these different types of hydrogens as A, B, C, and D, and I'm going to match them to their appropriate peaks. So we'll start with the alcohol. I'll call this hydrogen group A. There's 1 hydrogen in this group, which would correspond to the peak containing 1 hydrogen. Now this peak falls under the normal chemical shift for alcohols, and also it is not split because alcohol hydrogens do not participate in splitting or the neighbor rule. So this peak makes sense. Next, we have 2 hydrogens here. I'll go ahead and call them group B. Now these 2 hydrogens are very close to the oxygen. Because they're close to the oxygen, it would make them come out further to the left. Now if we take a look at this peak more towards the left, it is made up of 2 hydrogens. We can also verify the splitting. We see 3 splits here and 3 splits, a triplet, means that this group of hydrogens has two neighbors. Since two neighbors plus 1 means that the peak would be split into 3. So all of this makes sense for our group B hydrogens since they have two neighboring hydrogens. And the hydrogen on the oxygen does not participate in splitting, so we just ignore it. Next, we have another group of two hydrogens. So I'll go ahead and call these group C. Now we have one more peak that is associated with two hydrogens. And again, let's go ahead and verify the neighbors or the splitting. So we can see that this peak is split into quite a bit. We have 1, 2, 3, 4, 5, 6 splits that we can possibly see. So that means that this group of hydrogens probably has around 5 neighbors. Okay, and the splits may not always be clear, but what we can see here is that this group of hydrogens does have several neighbors. Now looking back at our structure, we can see that the groups that we have, so this is the group that we're focusing on, has 1, 2, 3, 4, 5 neighbors. Right? So all of that makes sense for this last peak. So then lastly, we have group D, which is 3 hydrogens, representing this peak here. And again, these hydrogens have 2 neighbors. So 2 plus 1 means it'll be split into 3, which we can see on the graph right there. So this is the approach that we're going to be taking for the large part of our worksheet for this lab. So your assignment for this lab is broken up into 4 main parts. First, you're going to be practicing calculating the degree of unsaturation, and you're going to draw 3 possible structures for each molecular formula. I want these all to be constitutional isomers. And they can either be drawn as Lewis structures or bond line structures. Second, you're going to be matching structures to NMR. So you're going to be given 9 structures and 9 NMR spectra, and you're going to have to match each structure to each spectra. Please make sure you read the instructions carefully and complete all steps. There are 4 different things you need to do for every NMR spectrum. Then you'll have 2 multiple choice problems. With these ones, you'll be given 4 possible molecules, and you'll also be given the IR and the NMR data, and you'll have to match one of the molecules to both pieces of data. And lastly, you'll be practicing carbon NMR, so you'll be given several molecules. You just have to predict how many signals you would expect to see depending on the number of different types of carbons in the molecule. Make sure that you print out the chemical shifts sheet and also take note on the process that I outlined for matching molecules to NMR spectra.